students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as interference of light. Let's do the numericals of interference of light, guys. Take on please. The path difference between two identical waves, arriving at a point, the path difference between two identical waves arriving at a point is 85.5 lambda. Is the point bright or dark? If the path difference is 42.5 micrometers, calculate the wavelength. Now guys, I can say that, guys, see this, path difference is 85.5 lambda, which can be written as 171 into lambda by 2 and multiplied by 2 I divided by 2. Why do I do that? Whenever you have a decimal number, multiply by 2, divide by 2, right? Guys, in simple language, especially for those of you who are doing CET, you generally get this question in CET also. Is the point bright or dark? If you have a decimal answer, if you have path difference with a decimal figure, it's a dark point. If it's a whole number, it's a bright point. Or you can conversely say it as multiply this by 2. So 85.5 multiplied by 2 is 171. Since I'm multiplying by 2, I have to divide by 2 also. So I multiplied by 2, I divided by 2. That means I'm getting the path difference to be an odd multiple of lambda by 2. 171 is an odd number and it's a multiple of lambda by 2. You will say as the path difference is an odd multiple of lambda by 2, therefore the point is dark. This is how you find out whether it is a bright point or a dark point, right? In simple language, guys, as soon as you look at the sum, if you get point something, 0.5, that means it has to be a dark point. Next, I can also say that path difference is given to you as 42.5 micrometers. That means I can therefore say that 85.5 lambda is 42.5 into 10 raised to minus 6. Therefore, you could say that lambda is 42.5 into 10 raised to minus 6 upon 85.5. When you simplify this, you will get this answer as 4971 into 10 raised to minus 10 meters. So the wavelength is 4971 into 10 raised to minus 10 meters. Fine. Take down next one, please. The distance of a point on the screen, from two coherent sources, differs by 93 wavelength. Is it bright or dark? Is the point bright or dark? If the path difference is 0.0465 millimeters, 0.0465 millimeters, calculate the wavelength. Now guys, see this path difference 93 lambda. There's no decimal point here, so straight away I can say that path difference is integral multiple of lambda. Since it's an integral multiple of lambda, therefore I can say that the point is bright. They've given you path differences 93 lambda. They've also given you path differences 0.0465 millimeter. To convert it into meters are multiplied by 10 raised to minus 3. So in which case I will get lambda is 0.0465 into 10 raised to minus 3 upon 93, which works out to 5000 Armstrong units. 5000 into 10 raised to minus 10 meters, which can also be written as 5000 Armstrong units. Right? Take on next one, please. A point is situated. A point is situated at 6.5 centimeters. At 6.5 centimeters and 6.65 centimeters. A point is situated at 6.5 centimeters and 6.65 centimeters from two coherent sources. Find the nature of the illumination Find the nature of illumination if the wavelength of light used is 5000 Armstrong unit. If the wavelength of light used is 5000 Armstrong unit. Now they're saying a point is situated at 6.5 centimeters and 6.65 centimeters. That means how much is the path difference? 6.65 minus 6.5, that is 0.15 centimeters. That is 0.15 into 10 raised to minus 2 meters. That is your path difference. Right? Now, I can say that path difference is 0.15 into 10 raised to minus 2 meters. Lambda is given to you as this. I can say path difference is given by the formula n lambda. That means 0.15 into 10 raised to minus 2 is n into 5000 into 10 raised to minus 10. So 0.15 into 10 raised to minus 2 upon 5000 into 10 raised to minus 10 is n. When you simplify this, you will get this answer as 3000. N is going to be 3000, which is an integral number. That means I'm going to get, I can say therefore, path difference is n lambda. N you found out as 3, so 3000 lambda. Therefore I can say that which is an integral multiple of lambda. Integral multiple of lambda. Since it is an integral multiple of lambda, therefore it has to be a bright point. Unless and until it's an odd multiple of lambda by 2. Only if it is an odd multiple of lambda by 2 will it be a dark point. Otherwise it will be a bright point. I can say therefore the point is bright. Next. Take on next one please. In a biprism experiment. Next one. In a biprism experiment, the screen is placed at a distance. The screen is placed at a distance of 1 meter. light of 4200 Armstrong units is used. Light of 4200 Armstrong units is used, and the distance between the two slits is 2 millimeters. A point P is situated at a distance of 4.2 millimeters from the center. 4.2 millimeters from the center. Is the point right or down? Guys, let's see this. Now, path difference can also be given by the formula. Path difference is nothing but x d by d. Path difference is also given by the formula x d by d. When the distance of the given point from the center of the screen is given, then path difference is given by the formula x d by d. So I have the value of x, which is 4.2 into 10 raised to minus 3. D, small d is 2 into 10 raised to minus 3 upon d, capital D is 1. So this is going to be 8.4 into 10 raised to minus 6. Right? Now, once I have this, then I can say that path difference is also given by the formula n lambda. You found out path difference to be 8.4 into 10 raised to minus 6 is n into lambda. Lambda you've written as 4200 into 10 raised to minus 10. In which case you will get the value of n to be 20. Right? That means I can therefore say that path difference is 20 lambda, which is nothing but it is an integral multiple of lambda. Since it is an integral multiple of lambda, therefore the given point is right. Fine, do we get this thing here? Next. Take on next one, please. In Young's experiment, wavelength of light is 6000 Armstrong unit. Wavelength of light is 6000 Armstrong unit. The path difference of point P. In Young's experiment, the wavelength of light is 6000 Armstrong unit. The path difference of point P on one side of the central bright band, the path difference on one side of the central bright band is 0.0075 millimeters. Is 0.0075 millimeters, and point Q on the other side, is 0.0018 millimeters. how many bright and dark bands are there between P and Q? How many bright and dark bands are there between P and Q? How many bright and dark bands are there between P and Q? Guys, we know that path difference is given by the formula n lambda for point P. Path difference is given to you as 0.0075 into 10 raised to minus 3 is equal to n lambda is 6000 into 10 raised to minus 10. So NP, number of n for P is going to be, when you solve this, you will get this answer as 12.5. You will get the value of n as 12.5. Next, for point Q, I can say path difference, that is 0.0018 into 10 raised to minus 3 is NQ into 6000 into 10 raised to minus 10. So when you solve this, you will get the value of NQ to be 3. Since point P and Q are on opposite sides of the central bright band that's given to you in the sum, since points P and Q are on the opposite sides of the central bright band, therefore they will ask you how many how many points are there between P and Q. So number of bands between P and Q, from central bright band to P there are 12.5 bands. From central bright band to Q on the other side there are 3 bands. So there are going to be total 15.5 bands between P and Q. Right? 3 bright bands and this 12 bright bands and 1 dark band. Fine, do we get this? Take on next sum please. In Young's experiment, the distance between two slits is 0.8 millimeters. The distance between two slits is 0.8 millimeters. And the distance of the screen from the slit is 1.2 meters. If the fringe width, I hope you all remember what is fringe width. Fringe width is the distance between two consecutive bright bands or two consecutive dark bands. If the fringe width is 0.79 millimeters, calculate the wavelength of light. Straightforward sum. Wavelength of light, x is xd by d, right? You have all the 3 values. You have fringe width, you have distance between the slit and the distance of the screen. Straight substitution, you should get the answer. The answer for this should be 5267 Armstrong unit. Answer, I'm not solving this. 5267 Armstrong units. Next, take down next one please. In Young's experiment, the distance of the screen is 1.5 meters, and that between the slits is 0.15 millimeters. light of 6,500 Armstrong units is used. Light of 6,500 Armstrong units is used. Calculate the fringe width. Calculate, first part of the question, the fringe width. Second part of the question, the change in fringe width if the screen is taken away from the slit. If the screen is taken away from the slit by 50 centimeters. If the screen is taken away from the slit by 50 centimeters. Guys, first part of the question, fringe width. Fringe width is nothing but lambda d by d. Straightforward, all the three values are given. Now guys, in this experiment, let's visualize the experiment. This is my Young's experiment. This is my distance between the two slits, d. This is the distance of the screen, d. And wavelength of light used is d. Now they are saying that the screen is moved away from the slit, right? The screen is moved away from the slit by another 50 centimeters. Now 50 centimeters is nothing but 0.5 meters. That means if I move the screen away from the slit by another 50 centimeters, the new value of capital D will be 2 meters. Do we understand this? So I can say for the second part of the question, I can say D is 2 meters. Balance, everything else remains the same. So again use the formula. Fringe width is nothing but lambda d by d. Right? Here you will be using d1. Wavelength of light and the distance between the two slits has not been changed. Substitute the values. You will get x1. They have asked you to find out the change in fringe width. Change in fringe width is going to be nothing but modulus of x1 minus x. Right? You have the value of x1, you have the value of x, you should be able to get this. The answer for this should be the change in fringe width you should get as 2.167 millimeters. Right? Next, take on the next one please. In Young's experiment, interference bands are produced on the screen placed 1.5 meters from two slits separated by 0.15 millimeters. Light of 4,500 Armstrong units is used. Light of 4,500 Armstrong units is used. Find the fringe width. And the change in fringe width. Find the fringe width and the change in fringe width if the screen is brought towards the slit. If the screen is brought towards the slit. If the screen is brought towards the slit by 50 centimeters. If the screen is brought towards the slit by 50 centimeters. If the screen is brought towards the slit by 50 centimeters. Replica of the previous sum. First thing I'll find out fringe width, first part of the question. Fringe width is nothing but lambda d by d, straightforward. Second part of the question. The screen is brought towards the slit. Now since the screen is brought towards the slit by 50 centimeters, that means now the value of d will be 1.5, 50 centimeters is nothing but 0.5. Now the value of d will become 1 meter, right? In the previous sum it was moving away from the slit, here it is brought towards the slit. So now I can find out the new fringe width, lambda d by d. Therefore I can find out the change in fringe width. Change in fringe width is going to be modulus of x1 minus x, right? Substitute the values, you should get the answer. The answer for this sum, change in fringe width, should be 1.5 millimeters. Take the next one, please. In Young's experiment, the screen is placed 1.5 meters away. In Young's experiment, the screen is placed 1.5 meters away, and the distance between the slit don't write that distance between the slit and the fringe width. Instead of distance between the slit, please write that as fringe width. And the fringe width is 6.5 millimeters. And the fringe width is 6.5 millimeters. The fringe width is 6.5 millimeters. What would the fringe width be? What would the fringe width be if the screen is brought towards the slit by 50 centimeters? If the screen is brought towards the slit by 50 centimeters. Now see, the screen is brought towards the slit. That means the distance is going to reduce. 50 centimeters means 0.5 meters. That means the new distance of the screen is going to be 1 meter. Right? Now we know that fringe width x is nothing but lambda d by d. Therefore I can say that x1 is lambda d1 by d, because they haven't said that neither is the wavelength of light changing nor the distance between the slit is changing. Similarly, I can say x2 is equal to lambda d2 by d. Divide the two equations, therefore I get x1 upon x2 is d1 upon d2. Lambda and d would get cancelled. Out of this I know three things. I know d1, x1 and d2. I should be able to get the value of x2. x2 will be nothing but x1 into d2 upon d1. Multiply and you should get this answer. The answer for this sum should be 4.333 millimeters. Next, take down next one please. Calculate the distance of the 30th right band. Calculate the distance of the 30th right band if the distance of the 15th right band is 6 millimeters. Now, for bright bands, I can say that the distance of a given band from the central band is nothing but n lambda d by d, right? So I can therefore say that x15 or x1 will be nothing but n1 lambda d by d. Similarly, I can say x2 is equal to n2 lambda d by d. Divide the two equations. If I divide the two equations, I'll get x1 upon x2. I will get x1 upon x2 is equal to n1 upon n2, out of which I know the value of x2, n1 and n2. So I should be able to get the value of x1. Answer for the sum should be 12 mm. Take down next one, please. In interference experiment, the distance between the slit is 0.3 millimeters. The distance between the slits is 0.3 millimeters and wavelength, the distance between the slits is 0.3 millimeters and wavelength of 5000 Armstrong units is used, and wavelength of 5000 Armstrong unit is used. If the distance of the screen is 1.2 meters, if the distance of the screen is 1.2 meters, find the bandwidth. First part of the question, find, first part, the bandwidth. Second part, the distance between the central bright band and the 10th bright band. The distance between the central bright band and the 10th bright band. Next part of the question, the distance between the central bright band and the 5th dark band. The distance between the central bright band and the 5th dark band. Next part of the question, the distance between the 10th bright and 5th dark band on the same side. The distance between the 10th bright and the 5th dark band. The distance between the 10th bright and the 5th dark band on the same side. Fine. Let's see the sum, guys. They said that in an interference experiment, the distance between two identical sources is given to you. They have also given you the wavelength. They have given you the distance of the plane, the distance of the screen. Now, the first part of the question, you have to find out the bandwidth, x. Right? Bandwidth is nothing but lambda d by d. So straightforward, I can get the value of bandwidth. Bandwidth is going to be lambda d by d. Second part of the question is the distance of the 10th bright band. N is equal to 10. So xn is given by the formula, bright band it is. N lambda d by d. For bright band, the distance of the nth bright band is n lambda d by d. So you have the value of n, so you should be able to get this. Next, the next part of the question is, third part of the question is the distance of the 5th dark band. N is 5. Now this is dark band. For dark band, the formula is xn is equal to n minus half lambda d by d. That's how you will get the distance between the distance of the 5th dark band. Next, they said that the distance between the 10th bright band and the 5th dark band on the same side. Since both are on the same side, therefore distance between 10th right and 5th dark band, we have already found this out. That will be x10 bright minus x5 dark. This is my x10 bright, this is my x10 bright, and this is my x5 dark, right? Just subtract the two, you should get your answer. Now the answers for this sum should be, bandwidth should come out to be 2 millimeters, 10th bright band should come out to be 20 millimeters, 5th dark band should come out to be 9 millimeters, and the distance between the two is going to be 11 millimeters, right? Next, take our next one please. In biprism experiment, the distance between the slit and the biprism, the distance between the slit and the biprism is 20 centimeters. And that between the biprism and the eyepiece biprism and the eyepiece is 80 centimeters. A convex lens is introduced between the biprism and the eyepiece. A convex lens is introduced between the biprism and the eyepiece. The images of the slit obtained in two positions are the images of the slit obtained in two positions of the lens are, or in the two positions are 2 millimeters and 4.5 millimeters apart. Wavelength of light used is 6000 Armstrong unit. Wavelength of light used is 6000 Armstrong unit. Find first part of the question, the distance between the 8th bright band and the 5th dark band on the opposite sides of the central band. The 8th bright band and the 5th dark band on the opposite sides of the central band. Second part of the question, the distance between the 5th bright band, and the 4th bright band on the opposite sides of the central band. And third part of the question, the distance between the 7th dark band, and the 4th dark band, the distance between the 7th dark band and the 4th dark band on opposite sides of the central band. Now guys, they've given you that the distance between the slit and the biprism is 20 centimeters and that between the biprism and the eyepiece is 80 centimeters. That means the slit is at a distance of 100 centimeters from the eyepiece. 100 centimeters is nothing but 1 meter. Now the two pole positions are given to you, or the two positions in which you are getting the, once you move the convex lenses, are at 2 and 4.5 millimeters. Therefore, I can say that the distance between the slits is square root of d1 into d2. We've done this derivation. That in biprism experiment, the distance between the slit is found out by the formula square root of d1 into d2. Once you have this, then you can find out everything. The first part of the question is that the distance between the 8th bright band and the 5th dark band on opposite sides. Since they are on opposite sides, you have to add the two distances. Now 8th bright band will be 8 lambda d by d. 5th dark band will be nothing but 5 minus 1 by 2 lambda d by d. For bright band it is n lambda d by d. For dark band it is n minus 1 by 2 lambda d by d. You have all the values, you can substitute and get this. Second part of the question. The distance between the 5th bright and the 4th bright band on opposite sides. The distance between the 5th bright and the 4th bright on opposite sides. Since they are on opposite sides, I have to add them. Since both are bright bands, I'll have to use the formula n lambda d by d. So this is going to be 5 lambda d by d plus 4 lambda d by d. Straight away you can do this as 9 lambda d by d. Last part of the question. The distance between the 7th dark band and the 4th dark band on opposite side. 7th dark and 4th dark. 7th dark will be 7 minus 1 by 2 lambda d by d. Since they are on opposite sides, you add. If they are on the same sides, you subtract. If they are on opposite sides, you add. 4th dark, 4 minus 1 by 2 lambda d by d. Right? Substitute the values and you should get the answers. The answers for this sum should be, for the first part, the answer is going to be 2.5 millimeters. For the second part, the answer should be 1.8 millimeters. And for the third part, the answer should be 2 millimeters. Right? Take down next one please. In biprism experiment, the distance between the slit and the eyepiece, is 1 meter. The distance between the slit and the eyepiece is 1 meter. Wavelength of light used is 5600 Armstrong unit. Wavelength of light used is 5600 Armstrong units. Two convex lenses are kept at a distance. Two convex lenses are kept at a distance of 30 centimeters from the slit. That's my distance of the object from the slit. And the distance of the two virtual images are, the distance between the two virtual images are, the distance between the two virtual images are 0.7 millimeters. The distance between the two virtual images are 0.7 millimeters. Fine. First part of the question, the bandwidth. Second part of the question, the distance between the 8th bright and the 3rd bright point. The distance between the 8th bright and the 3rd bright point on the same side of the central band. Next, the distance between the 5th dark and the 2nd dark band on the same side of the central band. The distance between the 5th dark and the 2nd dark band on the same side of the central band. Fifth dark and 2nd dark on the same side of the central band. Now let's try to understand the sum, guys. This is the slit, this is the eyepiece, right? They're saying that in a biprism experiment, the distance between the slit and the eyepiece is 1 meter. Okay? You will have a biprism somewhere here. Okay. Next, they've said that a convex lens is kept at a distance of 30 centimeters from the slit. This distance is given to you as 30 centimeters. Now if this distance is 30 centimeters and the total distance is 1 meter, 1 meter means 100 centimeters. That means the distance between the convex lens and the eyepiece is going to be 70 centimeters. Right, people? Do you understand this? Now distance of the object is x and distance of the image is therefore going to be 70 centimeters, that is 70 into 10 raised to minus 2 meters. Now if you remember your derivation of distance between the two slits in a biprism experiment, I can say that d1 upon d is nothing but y upon x. d1 upon d is nothing but y upon x for a single position of convex lens. This is how you find out the value of d, right? Now, once you have done that, then you can say that once you have d, then remaining is very straightforward. You have to find out first part of the question, fringe width. Fringe width is lambda d by d. Second part of the question, the distance between the 8th bright band and 3rd bright band on the same side. Since they are on the same side, you will have to subtract bright band. That means it is going to be n lambda d by d, n lambda d by d minus n lambda d by d. This is going to be 5 lambda d by d, right? And next part of the question is distance between the 5th dark and the 2nd dark on the same side. 5th dark and 2nd dark on the same side. Since it's on the same side, you will have to subtract. Since it is dark, it is going to be n minus 1 by 2 lambda d by d. So 5 minus 1 by 2 lambda d by d minus 2 minus 1 by 2 lambda d by d. Right? You should get the answer for this as the answer for the first part, that is my fringe width, should come out to be 1.867 millimeters. And second part of the question, the distance between the 8th bright and the 3rd bright should be 20.53 millimeters. And the third final part of the question, the distance between the 5th dark and the 2nd dark should be Guys, the answer in my book is wrong. You'll have to check this, the second and the third part. Right? You have 1.867, you'll have to calculate and get the answer for this. Right? Next, take on next one please. In biprism experiment, the eyepiece is kept at a distance of 1.5 meter from the slit the distance of the two dark bands from the central point, the distance of the second dark band from the central point is 1.2 millimeters. The sizes of the magnified and diminished images are 2.4 millimeters and 0.6 millimeters. Find the wavelength of light used. First of all, they've given you the heights of the magnified and the diminished images. So I can find out the distance between the two slits. The distance between the two slits will be square root of d1 into d2. Once I know the distance between the two slits for a dark band, we know that xn is equal to n minus 1 by 2 lambda d by d. So x2d, second dark band, will be 2 minus 1 by 2 lambda, we don't know, d by d, d and d we know. So if you substitute here, lambda is the only unknown here, you should get the value of lambda. The answer for this sum should be 6400 Armstrong units. Next, take on next one please. In biprism experiment, the distance of the screen from the slit is 1 meter. The distance of the 30th bright band is 0.6 centimeters. A convex lens is placed at a distance of of 20 centimeters from the slit. 20 centimeters from the slit. What is the wavelength of light used? If the distance between the two virtual images is 1.2 millimeters. The distance between the two virtual images is 1.2 millimeters. Okay, Guys, let's see this. The distance of the lens from the slit is 20. So in that case, the distance of the convex lens from the eyepiece is going to be 1 meter. That means 100 centimeters minus 20, 80 centimeters. That's 80 into 10 raised to minus 2 meters. Right? Once I know the distance of the image from the lens, I have y. I can find out the distance between the two slits. The distance between the two slits d can be given by the formula d1 upon d is y upon x. From here I'll come to know the distance between the two slits. Now they've given you the distance of the bright band. For bright band, I can say that xn is n lambda d by d. So x30 bright is going to be 30 lambda d by d. I know everything except lambda. I should get the value of lambda from here. The answer for this sum should be, the answer is going to be 6 into 10 raised to minus 8 meters. Right? Okay. We'll do one thing. We'll stop this here for the day. Thank you very much.